Ready to go? Cool. Alright, so second talk. This afternoon we're going to chat about doing efficient lookups of IP addresses in LuaJIT and OpenResty. So we'll spend a bit of time going into our specific problem domain because something like IPv4 lookups is a problem that's been solved for like 30 years. So for us specifically, we had a case where we needed to search a very, very large set of CIDR blocks on the order of tens of thousands of CIDRs, typically coming from spam lists, BOA lists, things like that. In our use case, this was for IPv4 only, so not having to worry about the complexities of IPv6. And quite frankly, because I was lazy and didn't want to handle IPv6, so I just said, I'm only going to do it for IPv4. This was something that we were doing in a hot path in our infrastructure as part of low-hanging fruit. So we call it like the top of our stack implementation, where it was part of the first part of our security layer. So we really, really cared about performance. We wanted to get in, do our CIDR search, and get out very, very quickly. Not a whole lot of logic here, just checking, again, very, very large lists of IPv4 CIDRs. Get in, do the check, get out very, very quickly. We have a very, very small footprint in our infrastructure. These slides didn't quite format properly, so some of them are cut off on the bottom. It's a lot, Enrique. So it's the bottom bullet says regular refresh. Part of our use case was that we were getting CIDR lists coming in from various sources on a regular basis every couple of minutes or so. So statically defining them in a config file wouldn't work. We needed to refresh our sources regularly, and it needed to be done without reloading worker processes. So this is a great use case for OpenResty, being able to read something in on a recurring basis, apply it, keep that data in memory, and work on it when we need to without having to reload the worker, deal with configuration management across a geo-distributed cluster, anything like that. So OpenResty, woo! So part of our problem domain, again, was search-based. A lot of existing implementations of IPv4 lookups for OpenResty. We're going to look at some specific examples, use a linear search pattern, and when you get to the scale that we had, thousands, tens of thousands, or hundreds of thousands of lookups, that becomes very, very expensive. For most of our cases that we looked at, typically the nodes and the environments that we were working on had plenty of memory, so CPU usage was the bottleneck that we cared about in initial performance testing with existing solutions. We were just pegging CPUs. So we had plenty of space to cache data, so trading off memory for CPU usage, getting the most out of our CPUs and being as efficient as we could while working in a high-level language like Lua in our existing infrastructure was our goal here. So again, the goal was having a proper algorithm and a proper implementation, making sure that we were getting correct answers when we were doing IP lookups, but again, focusing on either using an existing implementation or writing our own algorithm that would be as efficient as possible. So some existing implementations, the first thing when anybody says, hey, I need to look up an IP address or do a CIDR match in OpenResty is lua-resty-iputils. It was written by Hamish Forbes like 4 years ago. It's like probably one of the most common OpenResty libraries. It's on LuaRocks and OPM. It's out there. Like everybody uses it because people have to do IP lookups sometimes. So very battle tested, been in the community for a long time. It's a very simple interface. It offers transparent caching of parsing CIDRs, CIDR block ranges, and IP addresses through lua-resty LRU cache. So saving cycles there, and again, that's built into the API, so that's abstracted away from the caller. One of its bigger weaknesses, in addition to speed concerns that we had, is that it is IPv4 only. Again, for our use case, we weren't worried about IPv6, but when looking at existing solutions, we wanted to look at not only performance but feature set as well. So it's kind of not for our use case, but when you're looking at various lookup sources, something to be aware of. And in the docs for lua-resty-iputils, there's a note at the bottom that says if you want IPv6, go look up lib-CIDR-FFI. And of course, this is cut off on the bottom, so when we post the slides online, we'll be able to see lib-CIDR-FFI has minimal bindings for the lib-CIDR project, which is a small C library that is used for miscellaneous IPv4 and IPv6 address lookups, two-string function operations, things like that. So this is a really minimal C binding. There were some performance limitations within lib-CIDR itself that we got concerns with, and we'll dig into that a little bit as well. There are also a couple of other things that we looked at in the OpenResty world. One of them is a library called Mediator, which Calm uses. There are no docs that I can actually find on this. When you go to the mediator page on GitHub, it says, please visit the doc page, and that 404s. There's no inline caching, there's no documentation, so we weren't even going to bother testing this out when we were looking at this. Can't find the docs, can't actually find usage examples. This is something that pretty much flew under our radar right away. The other thing that we wanted to look at was how the Nginx access module does IPv lookups. Figure Nginx has been around for a long time, written by really smart guys, really tuned for performance. So they're probably going to be doing something really smart and efficient with IPv4 and IPv6 lookups. So we wanted to use that as an example as well. We ran into some surprises along the way. So we'll dive into these examples really quick. Using lua-resty-iputils is very straightforward. There's a handful of functions to call, but the most efficient one is a function called inip-insiders. You take a binary representation of the IP address, and that's something that's provided by the Nginx interface for you, and a list of pre-parsed CIDRs that would typically be fed in by either a recurring timer or a block init or init by Lua or init worker by Lua. And the call here is very, very simple. So you can stick this into a content by Lua block. One function call just returns a Boolean true or false. Is this IP address in this block of CIDR? So very, very easy interface. That's, I think, one of the reasons that makes it so attractive. Very easy to install, very easy to start using right away. Simple call, simple return values. So we started doing some performance testing. And again, so hitting this, I set up, I reran these slides for this test this morning. So this is just on all the benchmarks that we're going to see are on a single worker process on an i7 laptop. This location that we hit is the same thing that we see down here. So again, what we're looking at is just loading REST-iputils and calling inip-insiders with the binary remote address. And in this example, the CIDR block that we've defined was a global, just for simplicity, but that's something that's been pre-calculated in the interface. We ran through this, really not impressed with the performance that we saw. Over 10 seconds, we hit 11,000 requests a second, so 1,000 and change requests per second. So 11,000 requests in 10 seconds. So a little over 1,000 requests per second. Just with that call, no backend calls. This was just a straight content by Lua block. So really expected to see a lot more performance out of the library that would expect is pretty small and really widely used. So this was a huge concern for us when we initially started looking at scaling out our CIDR lookups. This is cut off again, so we can't actually see the whole thing, but this is what the actual BinIP CIDR lookup looks like. So there's a little bit of bit ops to get a integer value of what the binary remote adder Nginx variable looks like. And the call is a linear lookup to all of the CIDRs that have been passed into the function, just a simple ipairs lookup. CIDRs in lua-resty-iputils are represented as a table with two values, the low bit value of the CIDR and the high bit value of the CIDR. So everything is just treated as an integer in this library. And the way that it determines a match is if the given search value, binary IP address, is greater than the bottom of the given CIDR and less than the top of the given CIDR. If you're somewhere inside of that NetApp block, then you have a match. Otherwise, this just falls out and returns false. Something again that I want to highlight, this is a linear implementation that loops over every single CIDR block. So as we start scaling out to 1,000, 10,000, 40,000 IP addresses, this is where our bottleneck is going to start to run in. This is a very, very efficient process. It's just a couple of mathematical operations, but you start doing this hundreds of thousands of times a second for 40 or 50,000 iterations. It's a lot of CPU cycles to do the same math ops over and over again. Some heuristics from the system tap toolkit that we took while doing some benchmarks. Enrique talked about some of the system tap tooling earlier this morning. This is a histogram that shows how much time we spent in the Lua VM across all of the phase handler inside of the Nginx process. In this case, it's only content by Lua. Because this is a really simple benchmark, we can clearly see how long the lua-resty-iputils library takes. So on average, min, average, and max values, these are microseconds. We're spending 837 microseconds, almost a full millisecond per request inside of our Lua handler, which is way, way, way longer than you would expect to see. And then some other data about what the Lua VM is doing. The LuaJIT VM, so in this case, 81% of samples that were collected by the system tap toolkit were compiled by LuaJIT. Most of the remaining values were C code, and that comes through just accessing the Nginx C API and things that aren't exposed out by, or exposed via FFI by lua-resty core. So the code here is saying it does JIT compile. I think that's one of the pitfalls that I've seen for myself and other developers when looking at performance benchmarking of LuaJIT code. So you say, oh, well, it doesn't trace support, LuaJIT compiles, so therefore it's going to be fast code. That's not always the case. The code does compile. There's no NYI operators in lua-resty-iputils. That doesn't mean it always performs necessarily well. Part of the LuaJIT docs that talk specifically about writing performant LuaJIT code mentioned specifically it's not always whether or not the code compiles or not. We're paying more attention to the fundamental algorithm design and not the minutia of what LuaJIT VM is doing is far more important. That's exactly what we see here, and we're going to continue to see that as we go on. So the next implementation we looked at again was libCIDR FFI. There's a little bit of boilerplate code in here for defining the binary IP value of the remote address, again, because lua-resty-iputils did that for us. We didn't need this boilerplate code. This is just a simple LRU cache to cache the value of our local host address, the client address that's coming in that we're checking against. One of the big problems with libCIDR is that the only function that's exposed that actually does CIDR lookups is this function called contains. And this takes a single CIDR block that in this case we have to loop over in a table and our binary IP address. So instead of being able to provide a target IP and a list of CIDRs, we need to make this function call for each and every single CIDR block that we need to make, which is now an additional, in this case at our scale, about 40,000 IP addresses. That's 40,000 calls that we need to make from Lua into C via FFI. And our performance results were an order of magnitude, whereas here only 160 requests per second that we were seeing in the same block. So clearly this is not going to work for us at any scale either. So again, the other thing that we've looked at was trying to dig into the Nginx access module and figure out how they handle ACL lookups. Again, the static config maker wasn't useful for us, but we just wanted to see if there's anything we could learn from them. So they may be doing some sort of algorithmic implementation, something to speed it up. And the answer is no. It's just a really simple linear loop, and that was surprising. I anticipated something a little bit more advanced, and that module turned out to be very, very simple. The loop that actually does checking for IPv4 lookups is just the same iterative loop that we would have seen in lua-resty-iputils, looking through all of the defined ACL blocks that are in your Nginx config, and then doing the comparison. And if there was a match, then you would act based on how the module was configured. The difference between iputils and what Nginx does, where the actual check is done, was interesting to us. The way that this reads out is the binary address and the net mask of the ACL are binary handed. And if that matches the address portion of the CIDR block, which is the lowest IP you can have in the CIDR block, then that IP is considered a member of that CIDR. We're going to dig into that in just a second. So this kind of piqued my curiosity a little bit, and I wanted to see if these bit-offs would be more efficient because there's less branching here when it would compile down to LuaJIT. So we did, as we'll see with our implementation, we did essentially, I want to say take a page, but we essentially copy and pasted this code in this check, and that's how we end up running through our implementation. The way that Nginx represents CIDR blocks is just a struct with two initters, which are just unsigned 32-bit integers under the hood. So there's one integer for the address and one for the CIDR mask. So some takeaways from our initial research. The individual searches are not that expensive. Doing lookups when IP addresses are converted to integer representations is very slow. It's just very, very fast, just integer math. So what we wanted to focus on was maintaining a small call footprint, and if we could find any solution that meant that we weren't doing a linear loop over 10, 20, 30, 40,000 different CIDR blocks. But as I mentioned earlier, if you're looking at the output of the LuaJIT command line utility with the dump flag turned on, just because something JITs doesn't necessarily mean that it's an efficient algorithm. So that was a focus for us as well. So we wanted to come up with our new approach. We thought, all right, well, 40,000 iterations is a lot of iterations. What if we can make that smaller? I mentioned a little bit yesterday, I don't have a background in computer science. My background is systems administration and engineering. So a lot of this was an exercise in CS 101 stuff about what is binary search? How does that actually work? And to me, that was really, really interesting, and I'm pretty sure this is all really boring for everybody that did this in college 10 years ago. But for sysops guys, it was fun to dive in and do something that was a little bit more theoretical. What we wanted to focus on was reducing the amount of time that it took to find the right CIDR block that we wanted to match. Rather than examining every single CIDR block, we wanted to find a way to minimize the time that it took to match one CIDR, finding the correct CIDR, as it were. And it turns out that doing a binary search, logarithmic time is our friend. I think this slide got cut off, but when you, in the case of like 40,000 iterations, log 2 of 40,000 is like 13. So imagine doing something 13 times instead of 40,000 times. It's going to be a lot faster. So again, some quick review of how IPv4 addresses are formatted. There's two portions to an IPv4 when you look at the 32 bits. The first chunk of bits represents the network portion of the IPv4. The second chunk represents the host bits. CIDR notation is just a human-readable way to look at both an IP address and its net mask. So when you have something like 192.168.0.0, the /24 of that, at the end of that means that the first 24 bits of that address represent the network value of that IPv4. The remaining bits, in this case 8 bits, represent the host portion of that. It's because some of these slides got cut off. I think we're going to have to just skip through some of these examples really quick. But this is an example. So if we have the IP 192.168.143, the bottom line here is the binary representation of this. The top line here is the netmask. So again, the first 24 bits of this address represent the network portion, and the remaining 8, when we're looking at CIDR blocks, we don't actually care about because we just care about what are the bits that make up the network inside of the CIDR block. And because this got cut off, I'm going to have to wing it as far as these examples go. So if we say, all right, we ask, is the IP 192.168.143 inside of the CIDR block? In this case, 192.168.2.24. So the CIDR block is represented here on the second line. The net mask representation is on the first line, and the IP address, the address itself, is written in green, is on the bottom line. This is not really a meaningful graphic without the rest of the slide to get through, so I don't know. I think we're probably just going to have to skip through this. What we were trying to show here is that when you take the binary and of the network address, the bits related to the network address. See if Enrique can save the day here. Hey, look at that! Woo! He's a hero. So when we binary and the CIDR block with the relevant binary and the IPv address with the net mask portion of our CIDR block, what we end up is this first line, or rather the second line that's on the bottom, where the net mask here contains a 1 at the end. And essentially, what you would find is when you're looking at each individual bit, when an IP address is found inside of the CIDR block, the net mask portions are going to line up. So because these two values don't line up here, the IP address at the top isn't inside of the ACL that we see at the bottom. Contrast this with the second example. We have the same IPv4 address, but a slightly separate CIDR block /23. So in this case, 23 bits are used to represent the network portion, 9 bits represent the host portion of the address. Again, when we binary and the first 23 bits of our net mask and the IPv4 address, and then compare that with the net mask value of the CIDR block, when those two values are the same, which is what we see at the bottom, that's an indication that our IP address is a member of the CIDR block, and we can take advantage of this and perform a quick calculation to determine whether or not a given IP is inside the CIDR block, and that's exactly how Nginx does its lookup and its access module. So, in doing a binary search is useful when you're looking for an individual element. But in our case, our elements, which are CIDR blocks, contain two values: the net mask, the mask portion of the CIDR block, and the bottom element, the network value of the CIDR block. Essentially, the portion of the CIDR block where all of the host bits are masked out to 0. So what we want to look for is a case in our giant list of 40 or 50,000 CIDR blocks where our integer, our IPv4 address that we're searching for, is greater than a CIDR's network value, but it's lower than a CIDR's broadcast value. And the broadcast value is when all of the bits are masked to 1. So the challenge is figuring out which one of these CIDR blocks that we want to look at instead of just looking at all 40,000 of them. So the idea, this is kind of a janky visual representation of this. So if we consider the top line just a number line from 0 to 2 to the 32nd, basically every possible integer that could be represented as an IP address. And we look at CIDR blocks. What we care about is if we consider a CIDR block to start at our number line where we have a red cursor, and then the CIDR block contains all integers through the black cursor. We basically want to find the block of integers where we fit inside of this value. So we want to get our binary search to a point where we're larger than a red value, but then lower than the next upcoming red value, and continue to binary search down until we only have one possible CIDR candidate. And then our lookup is whether or not we fit inside of the CIDR block, and if we fall outside of the CIDR block, then we don't have a match. This is essentially a duplicate slide, and I'm pretty sure I was supposed to cut it out, so we're going to skip this. Our representation of CIDR blocks that we look up is a Lua table, which is actually just an array of FFI structs for reducing memory usage. Again, it's two values, so consider the top, just as an example, is a human readable representation of the network address of the CIDR, and then the number of bits. What this actually gets translated to under the hood is just two integer values that get represented. The integer value representing 10.0.0.0, and then the integer value representing the net mask. And these are typically very high because net masks are all 1 followed by all 0s. This is our definition of what our struct looks like. This is essentially a ripoff of what Nginx defines for IPv4s in the hood. One of the annoying things that I found with FFI, LuaJIT FFI, is that it auto-defines some of the headers that you would find in systems, but some things like inet and whatnot aren't in there. So you would think like inat or t. This is a very common type def that almost everybody uses. Nope, you need to type def it yourself. So it would be kind of nice to see that global scope of definitions in LuaJIT's FFI expanded a bit to try to avoid some boilerplate like this. One line of code, not a big deal, but it's often very tricky to remember what's already been typed up now for you and what you need to add in yourself. So this is our binary search function in Lua. So we take an integer IP address, an FFI array of CIDRs, and a length of CIDRs, and we start bisecting. I'm not going to walk through the whole function because I'm sure everybody here has written a binary search function before. Essentially what we do is bisect if select if we need to. If we end up being larger than both our current bisect point and the next CIDR will bisect. Otherwise, if we're only larger than our current bisect point, we're potentially in a candidate CIDR block, and that's where we do our check. Doing a binary AND of our IPv address's value and the CIDR's net mask, and if that resultant is the same thing as the CIDR's network value, we're inside of our CIDR block, and we have a match. Otherwise, no match. So a binary search obviously requires that the array is sorted, which I had a little bit of fun playing around with at 1 in the morning when I didn't actually realize that table.sort doesn't sort FFI objects. So that was 45 minutes of my life that I'm never going to get back. So I ended up having to write a quick qsort that sorts based on the CIDR's network address and then based on the net mask. And the reason that we sort by net mask as a secondary part is for some optimizations that we're going to get into in just a second that relate to merging down superset or merging down subset CIDRs into supersets to reduce our search space further. So one of the optimizations that we had was forming a single CIDR for multiple IPs. And in our case, it's because some of our feed data was just large lists of individual IP addresses. And you had 1.1.1.1, 1.1.1.2, and this went on for 50 or 60 IP addresses. And there's no reason to consider each of those individual /32 CIDRs when they can be coalesced into a single block. So for example, 1.2.3.4 and 1.2.3.5 paired right next to each other just become 1.2.3.4/31. And the same thing with 24s or any size CIDR block, as long as the two adjacent CIDR blocks are the same size, and they would result in a clean CIDR that has no meaningless bits, we can merge them. And this work is done iteratively over and over again until there are no possible merges. So we're not just doing a single merge of two IPs into a /31 and then calling it quits. We continually loop over the array until there are no more possible merges. Part of the question that happens is, I mentioned meaningless bits. What happens when you have two IP addresses that are adjacent, but they don't form what we would consider a CIDR block? For example, the previous example, we had 1.2.3.4 and 1.2.3.5 becomes 1.2.3.4.31. If you try to follow the same logic with 1.2.3.5 and 1.2.3.6, you ended up with 1.2.3.5/31. That's not actually a meaningful CIDR because you have this dangling bit that is not part of a CIDR block. Again, the CIDR block's representation of the net mask or the network portion is when the host bits are all masked out to 0. So if we have a resultant CIDR that has any bits that are set in the host portion, not a meaningful CIDR, and we can't merge these two. So the case that looks like if you have 4 IPv4s in a row, 1, 2, 3, 4, 5, 6, 7, and 8, 6 and 7 can merge, 5 can't merge, and we can't merge anything with 8, so we end up with 3 CIDR definitions instead of 4. The other thing that we wanted to do, largely for efficiency, but also for accuracy when looking at adjacent CIDRs, was removing subsets of CIDRs. So we have a /24 and then a /25 that fits inside of that. Those two are functionally the same thing, so we only need to care about comparing the larger CIDR block. So again, a couple examples of what this looks like. 192.168.24 and the child 25 that's inside of it are just the same thing as 192.168. It should be /24 instead of .24. And again, this occurs in multiple cases with multiple children CIDRs that you go down. Essentially, the large parent CIDR wins. So this is our calling out our library. This is essentially what it looks like. The single function call that we have is just bin search CIDR. The binary IP address, again, we don't do any transparent caching of an integer representation of the IP like lua-resty-iputils does, because we ended up caching that elsewhere in our stack. So you pass in the integer representation, a table of CIDRs that we pre-generated, and the length, just so we don't have to pre-calculate the length or recalculate the length every single time. And the results here we were pretty impressed with. We also wrote, just for giggles and performance comparison, a linear search function, creatively called insearch CIDR, that uses the same type of pipe specs, but just uses a native ipairs loop instead of our binary search implementation. So reviewing our performance, lua-resty-iputils, we saw about 1,200 requests per second. LibCIDR F5 was about 160 requests per second. With our implementation, we saw, drumroll, 67,000 requests per second, which is several orders of magnitude of a very large number. Hey! So this was the goal, was finding a way to take a large subset of CIDR blocks and really rip through it as quickly as possible. One of the things, I'll get to that in a second. This is an example of histogram like we showed with the lua-resty-iputils function. We were averaging about 800, 850 microseconds of time in LuaVM. Here we're averaging 22. So again, more than an order of magnitude improvement. I was going to make a graph of the difference in time between our binary search lookup and our linear search lookup, but the scale became so dramatic that it was completely not meaningful. So when we're looking up 10 IP addresses, linear search actually took a little bit less time because there's more overhead for the JIT compiler to kick in and warm up for small chunks of IPs. But as we started to scale out by several orders of magnitude, looking up 40,000 IP addresses took 4 seconds for our linear search to look up and took 8 milliseconds for our binary search to look up. So again, chart of numbers, not really visually appealing, but at any sort of scale, the graphical representation is completely meaningless. So again, as I mentioned, our library assumes that the IP that gets passed in is just an integer. So caching that typically is handled in LRU cache, as lua-resty-iputils does. We just didn't write it in transparently, again, because it was handled in other parts of the stack. As I mentioned, there is a little bit of a warm-up, so searching less than a couple dozen or a couple hundred CIDRs probably makes more sense to just use something like lua-resty-iputils, something that's a little bit safer and not complicated. Again, this was a specific use case where we had a large set of IPs that we needed to search through in a very efficient manner. And again, no IPv6 support because our stack didn't support it at the time, and I'm lazy, and 64-bit ops and LuaJIT are apparently not a thing, which is a real bummer. And I would love to see that someday, but alas, we don't have it. No. Any questions?
So you said that you looked at what Nginx had internally. Did you look at what anything else had internally?
A couple of other things, but they weren't particularly relevant, largely because everything else is generally statically defined. Like bond security uses a tree implementation. A couple of other things I looked at. Like I think I looked at Varnish's implementation. But a couple other scalable server solutions that I looked at had the same problem where their ACL comparisons were either 2 CIDR blocks or a single IP and then another CIDR block, which didn't work for our case. So I think looking at mod-text tree implementation was part of the inspiration for this, was trying to figure out how can we turn this into divide and conquer and not just a brute force lookup. The idea here with this too was also not to introduce any additional dependencies, so doing all of this in pure religion. But yeah, there were a number of other things that I looked at that just weren't noteworthy enough to make the slides here. One thing that I did mention because the slide got cut off way at the beginning, another design target for us was to largely consider use cases where we weren't seeing any matches. We were looking at large blocks of CIDRs from Bogon lists, OpenBL, Fanhouse, things like that. But we had to consider the case where probably the vast majority of traffic was legitimate traffic. This is designed just to knock off low-hanging fruit and drop IPs that are pretty much guaranteed to be malicious, and we just don't need to see that traffic coming through our stack. But we have to consider the case that the vast majority of what we are going to see is legitimate traffic, at least from this perspective, and we want to consider the fact that we're going to be executing through our full search every time. So if you check our list of 40,000 IPs, and you put a CIDR block at the very top of that list, and trying to match that first, lua-resty-iputils is actually like 4 or 5 times faster than our implementation is, because that's just one single lookup versus all 40,000. So the benchmarks here were specifically targeted for worst case performance situations where we had to scan through the whole list every time because it's at the top of our stack, but we're assuming that we're not going to come up with a match. Sorry, skipped over that note when talking about our benchmarks over there. Any other questions? Yeah?
Hey, do you have a theoretical bound of so if somebody had written this like in a pure native module